So our next speaker this afternoon will be Ziquan Zhuang, if I've got that right, from MIT, who will speak on finite generation and K stability.
Okay, thanks for the introduction and for the invitation. It's my great pleasure to speak here. So I want to talk about, so this is like a complement to Chenyang's talk yesterday. So yesterday in Chenyang's talk, he gave a lot of description of the general picture. So I want to get to some of the more specific details. And particularly, I want to focus on two of the questions that was mentioned, maybe two of the topics that was mentioned in Chenyang's talk yesterday in K stability, and explain their relation to this finite generation in birational geometry. Okay, so let me first remind you those two questions. So the first question is this Yau-Tian-Donaldson conjecture. So in general, it states that if I have a Fano variety, it could have some singularities. Then the existence of so-called Kähler-Einstein metric. So Kähler metric with constant Ritchie curvature is equivalent to an algebraic condition called K polystability. So on the left-hand side, we get some analytic condition, while on the right-hand side, the equivalence tells us that it's given purely algebraically. Okay, but for this talk, for simplicity, I'll focus on a special case of this, which is more or less the general case, but just for simplicity, we'll focus on the case when the automorphism group of the Fano variety is finite. Okay, so the general case is very similar, just more technical, right? So in this case, the Yau-Tian-Donaldson conjecture just says that the existence of Kähler-Einstein metric, plus automorphism, always under this assumption, then is equivalent to a slightly stronger condition that the variety is K-stable. Okay, again, I'll give some more context on the definition to just as a reminder later, but this is the first question. Okay, so that's part one. The other question is about the construction of the modular space of Fano varieties. And I will only focus on the properties of this modular space. So eventually the statement will say that there exists a proper modular space parameterizing this K polystable Fano varieties. Okay, so I'll just write polystable and be abbreviated Fano varieties. Okay, so these are the two questions that I will focus on. So let me start from the first one. Okay, so the Yau-Tian-Donaldson conjecture.
X is always smooth.
It can be singular. Okay, so of course for singular varieties, one have to define Kähler-Einstein metrics appropriately, but assuming that can be done, then the statement is the same. Okay, so right, other questions? All right, so let's begin with the Yau-Tian-Donaldson conjecture. So for singular varieties, the way to attack this conjecture is by using the variational method, which goes back to this work of Mabuchi, and Chenyang also mentioned this in his talk yesterday. So Mabuchi discovered a functional that's now they call Mabuchi Synergy, and so it's a function on this space on H, which is so H is the space of Kähler forms that represent the first Chern class of the Fano variety. And as Chenyang mentioned yesterday, the reason we are interested in this space is because the Kähler-Einstein equation says that the rigid curvature of the Kähler metric is proportional to the metric, but Fano means that the constant is 1. But on the left-hand side, this always represents the first Chern class. Okay, so we have to choose the Kähler metric from this space to begin with. Right, and then Mabuchi discovered a function on this space, and it has the property that, so first of all, this energy function, if you look at the critical points, okay, so critical points of M, let me use a different pen. So this is much better. So the critical points of this energy function are exactly the solutions of the Kähler-Einstein equation, the solutions of that equation. Okay, so they comes from the Kähler-Einstein matrix. So that's the first nice property of this energy function. And another nice property, again discovered by Mabuchi, is that this M is convex along the geodesics. So I haven't told you what's the metric on this space, but Mabuchi introduced another so-called Mabuchi metric on this space. And whatever that is, this energy function is convex along the geodesics in that metric. Right, so what does this tell us? So the point is that, right, so if I give you a convex function and ask you whether it has critical points or not, then there are two typical pictures. So this one has critical points, while this one doesn't have critical points. And the difference between them is that, so if you look at their slope at infinity, so this one, the slope is positive, while this one is non-positive. Okay, so that means in general, if we want to get critical points for this convex function in an infinite dimensional space, the property we were looking for is that, so at least if I look at the slope at infinity of this Mabuchi energy function along a geodesic, so let's say omega t is a geodesic, one parameter family, I want this to be positive along geodesics. Because then I have hope to finding critical points for that function. Now we want to make contact with algebraic geometry, so we want to take approximations of this geodesics using algebraic geometric information. And that information is this test configuration. So let me erase some of the things on the top. So again, this was very briefly mentioned in Chenyang's talk yesterday. So test configuration, so which we will think of as algebraic approximation of geodesics. Right, so in some sense, a geodesic is a one-parameter family of Kähler forms in this space. So we can take something even stronger, which is a one-parameter family of algebraic varieties. So a test configuration for us, there are several different ways to think of it. So one of the interpretation is the family over the affine line, which compactifies, which extends the trivial family over the puncture, Gn equivariantly. Okay, so it has this Gm action, or maybe just write C star action, since everything in this talk is over C. Okay, and so it permutes these fibers away from the origin, and then but on the central fiber we are adding something else. Okay, so a typical example is like a singular quadric, a smooth quadric, and then you can degenerate to a singular quadric, something like that. Okay, so that's one way to think of this. It's a one-parameter family of algebraic varieties. But if I want to connect it to this context, another way to think of this is to take an embedding of my Fano variety into some projective space, so pluri-anti-canonical embedding. And then you choose some one-parameter subgroup in the corresponding PGL. Okay, and then so this sister action acts on this subscheme, and then you take the Hilbert scheme limit, we arrive at this GM equivariant family. Okay, now if I use this definition, then there's a canonical Kähler form on the projective space, the Fulbini-Studi form. So let me call this embedding rho. So then rho sub t will be my same embedding twisted by the C star action. Okay, so let's say t is in C star. So if I twist by the C star action and pull back the Fulbini-Studi form, maybe I need to rescale. Then this is in my space H, because I embed using the first Chen class times n. So if I put it there with scale, I end up in this space. Okay, so this is considered as the algebraic approximation of my geodesics. So this is a one-parameter family, but it's not necessarily a geodesics yet. But in any case, it makes sense to look at, again, the slope at infinity of my Mabuchi energy function along this algebraic race. So as Chenyang mentioned yesterday, so it's a calculation by Tian, also by Ding and Tian in the 90s, that if I look at the slope at infinity along this algebraic race coming from test configurations. Okay, so now so I guess you know what I mean, right? So so this limit exists, and it's exactly the so-called Futaki invariant of the test configuration. Okay, so where curly x is my test configuration, and so this number later on has an algebraic interpretation given by Donaldson, but that was the original way they discovered this. Okay, so then what's K stability? So by definition, being K stable means that this Futaki invariant is positive for any non-trivial test configuration. Well, non-trivial means that it's not a trivial family of X, right? Which makes sense because after all, we want the slope to be positive along geodesics. Now we have the algebraic ones. We want them to be positive along the algebraic ones. But now what's the difficulty in proving the Yau-Tian-Donaldson conjecture? Is one of the difficulty is that so the difficulty is that after all, these are only approximations of geodesics. And after we pass to the limit, it's not clear that so that the Futaki invariant being positive may not propagate to the limits, which are the geodesics. To the this infinity slope being positive along the geodesics. I mean, in the once we take the limit, right? So even assuming this slope has some continuity, in the limit, the limit of something that's positive may just be 0. So that's the main difficulty. And that so the first key observation that comes into the picture is that actually there's another way to take these limits of test configurations, but not in the analytic sense, just in an algebraic sense. And that is actually something that you heard in Morgan's talk, this Berkovich analytification, or more precisely, the valuation space that sits inside that Berkovich analytification. So the idea is that there's also another way to take limits of this test function. Maybe I should put that in quotes as valuations. So let me say very briefly how that works. So, so the idea goes back to the work of Buxon, Hisamoto, and Johnson. So they realized that, well, so one way to think about my test variation is that, so after all, I just need to add the missing central fiber. So let me take a component of the missing central fiber, x0. Okay, so this component. Then, so this component will give me a valuation on the function field of the total space of the test variation. And this is the divisor variation, so it takes values in Z. But I can also restrict this valuation. So because it contains X cross C star as the open set, this function field is nothing but the function field of my Fano variety, and I join an extra variable T, where T is the variable in the affine line. Right, so I can restrict this valuation to the smaller field, and let me call this V. And this is my valuation, okay, so associated to this component of the test variation. And in some sense, it determines the test variation because, so if I choose a valuation, a divisorial valuation on the function field, there is a unique C star equivariant extension to this bigger field. And if I know what are the divisorial variations, I know what are the divisors I'm extracting on the birational models. So in some sense, this determines my test variation, if I know the corresponding valuation for all the components. All right, so that's the first part. And another thing that comes from the work of Shi and Chenyang is that, so they show that in order to test K-stability, it suffices to use test configurations with a central fiber that's irreducible and actually a Fano variety with mild singularity. So KLT singularity, if you know what mild means. And that means I only get one valuation to worry about. So, right, so let's give it some name. So this will be some divisorial variation. And since the Futaki invariant is an algebraic invariant that's attached to this test variation, it's quite natural to believe that it's also an algebraic invariant that's attached to these valuations. So Fujita and Lee started to relate to write down expression for the Futaki invariant using these valuations, especially Fujita, but then later on also extended by Shirley, etc. So I think at the end of the day, what happens is that you can write down the Futaki invariant for this particular type of test variations. Let me give it. So this is really called special test variations. So for special test configurations, I think for this part, let's just Fujita. I think that's what he did. For special test variations, the Futaki invariant can be written up to some positive constant is given by the difference of two functions on the valuations. The first one is the so-called log discrepancy, while the second one is the expected vanishing order. Okay, so this is the log discrepancy. So we've seen this in Morgan's talk for divisorial valuations. And the second one is called expected vanishing order. So I won't define this more precisely. You saw it in Chenyang's talk using some integral expression. But one way to think of this is like this is the average of the vanishing order along V of when you restrict to this Q linear system minus K. Okay, so you take a basis of this and count what's the variation order of V along those spaces, then take the average values and look at asymptotic, etc., etc. So don't get into the specifics of this. All right, so at the end of the day, there are two natural functions on the valuation space, and the Fourier invariant is the difference of those two functions. Okay, so to begin with, for the Yau-Tian-Donaldson conjecture, we want to show that K stability implies the existence of Kähler-Einstein matrix. So at the beginning, we know that this function, or this function, is positive on divisorial valuations. Okay, so let me try to write that down. So according to this discussion, this will imply that the log discrepancy is bigger than the expected vanishing order for any divisorial valuations that comes from a prime divisor. But using this limit, so the limits are valuations. So Buxom, so I guess Berman, Buxom, Johnson. And later also by Shili, Chenyang Xu. So they show that if I extend this definition a little bit to include all the limit valuations, so they show that if the log discrepancy is bigger than the expected vanishing order for all valuations. Okay, so these are the limits in the algebraic sense. Then the conclusion is that Kähler-Einstein matrix exists. In other words, if I can take care of the limits in the algebraic world, I can also take care of the limits in the analytic world. That's what they did. Okay, so, but of course, there's a difference in between. Okay, so again, that led to this algebraic conjecture called the optimal destabilization conjecture. Yes. For this one, you need to assume it for all valuations. Yeah. But so the conjecture is that divisorial will be enough, right? So that's the natural way to conjecture. So, but the precise version is that, all right, so we need to have a way to make sense what do we mean by like divisorial variation are enough, right? So one way to measure the stability of a Fano variety using this invariant is to consider the infimum of log discrepancy over the expected vanishing order. Well, for all valuations. So I'll just use this notation for valuations over the function field. Okay, so then the conjecture is that if this number is less than or equal to 1, that's the case when that we'll consider. Then this infimum is computed by some divisorial valuations. So order along some divisor. So some divisor on some birational models of over X. Okay, so that's the optimal destabilization. So how this related to our context? Well, so the claim, of course, is that this conjecture plus their theorem implies the Yau-Tian-Donaldson conjecture. We'll get to that in the second part of the talk, so just bear with me. All right, so this optimal destabilization conjecture plus their theorem implies the Yau-Tian-Donaldson conjecture because, well, let's say the Yau-Tian-Donaldson doesn't hold, but it's also k-stable. That means there is some variation where this is equal. Okay, but if this is equal, then the delta invariant is at most 1. But I also know that the delta invariant is computed by a divisor variation, but it's at most 1, but that violates the k-stability condition. Okay, so once we know this threshold is computed by a divisor variation, I don't have to worry about the other variations. I just need to worry about the divisor ones. So then I can just apply this theorem. Okay, so it seems that is the conjecture that we need to worry about at the moment. Good, so that's halfway into the talk. So now the miracle is that the second question that I introduced at the beginning, that the properties of the K-modular space is also reduced to this same conjecture. Okay, so let me try to keep this on the board. Maybe I should move it a little bit up, but let me just leave it here. Okay, so I can leave the delta invariant. Okay, so what's the second part? So the second part is about the properties of the modular space. And for properties, obviously we want to prove properties using valuative criterion of properties from Hashon. In other words, what we are aiming to have is that suppose we have a puncture curve. Okay, so this C minus close point, and a family of K semi-stable Fano varieties over the puncture curve. Well, so K semi-stable means that Futaki invariant is always non-negative. Then I want to extend this family over the puncture to get a family, again another family of K semi-stable Fanos, even over the central fiber. Okay, so that's what we want. Okay, if we have this, then we have the properties of the modular space. Okay, so that's not easy. And maybe I can first remind you of some of the things that people did in the case of vector bundles to see what are the major steps that needs to be involved. So for vector bundles, so let's say modular space of K semi-stable vector bundles. What's a very good notation? Let me just write this. So let's say vector bundles over curve, just for simplicity. So there are several ways to show a modular space of a vector bundle, semi-stable vector bundle is proper, and one of them is an algorithm due to Langton. And the way this works is that, again, we use the valuative criterion. So we start with the family of vector bundles, semi-stable vector bundles over curve. And I want to find an extension, again, using semi-stable vector bundles. So I cannot do that at the beginning, but at least I can extend this to a family of vector bundles, right? I don't worry about the stability condition, but I can just push it forward to get the family of vector bundles. So now if the central fiber is semi-stable, I'm happy. Assuming it's not semi-stable, then we have the harder non-Riemann filtration, and in particular, we have the maximal destabilizing subbundle. So we can write down exact sequence. So G is the maximal destabilizing subbundle, and F is, of course, the quotient. Okay, so this is the maximal destabilizing subbundle. And Langton came up with this idea that if I modify this family a little bit, okay, so now I consider E prime is, okay, so when I write it like in this notation, E is the total family of the vector bundle. So I look at the kernel of E goes to F. Okay, so of course it factors through E0, but then it subtracts to E0, but I also have a subtraction from E0 to F. Okay, so if I look at this kernel of this composition, then I didn't change the generic fiber because this entire thing is supported on the central fiber. So then E prime is the same as E when T is not 0. But on the central fiber, I get something different. And if you analyze it carefully, because we killed this part, the E prime will have a quotient to G. Okay, so. And it turns out that the kernel is F. Okay, so what this suggests to us is that originally G is the maximal destabilizing subbundle, but after modifying this family, it goes to the quotient. So this indicates that stability improves. So let's say so E is like a vector bundle over this big family, right? So I don't know, like C cross another X. Okay, so E0 is the central fiber. So it maps to E0, but the E0 also subtracts to F. So I take the composition, right? So and because the maximal destabilizing goes to the quotient, stability usually improves, and that's what Langton shows. So Langton shows that using this algorithm, if you do this, if you continue,
no Stacy Langton, not
yeah, that's right, yeah. And this will terminate in finitely many steps, and at the end of the day, you produce a semi-stable vector bundle in this way. Okay, so this gives you the semi-stable field. Okay, so instead of just a vector bundle, I can get semi-stable vector bundle at the end. Okay, so of course, this is the old story, and now we have a different model space, which is the model space of vector bundles. But some parts of the story remain similar. So first of all, if I don't worry about the semi-stability conditions, I can extend this to a family of Fano varieties just by using MMP. And maybe up to base change, up to finite base change. So the idea is that after finite base change, I can do semi-stable reduction. I get a lot of components in the central fiber, but MMP allows me to contract most of the components. Eventually, I get one component, and if you do it carefully, that component will be a Fano variety. Okay, so this can be done. All right, so we are in this step, and now you want to say, all right, so assuming that central fiber is not semi-stable, I want to have an algorithm to improve the stability, an algorithm that stops in finitely many steps, and that's where this comes in. Okay, so to start this algorithm, we need to have a maximal destabilizing object, and that's given by this conjecture. Okay, so this is basically what was proven in the paper of Bloom, Kähler-Einstein, Liu and Xu. So they show that assuming this conjecture, we do have an analog of Langton's algorithm for the modular space of Fano varieties. Okay, so in some sense, it turns out that for modular Fano varieties, the hard part is the existence of a maximal destabilizing object, because it's unlike the vector bundles, there are only finite in some sense, like the slope, for instance, you only have finite many choices to worry about. But for Fano varieties, this infimum is quite mysterious. So you start with some divisor variations, and then we'll get something else, right? So let me try to sketch the proof of this. Okay, so I won't go to every minor details, but the idea, and then you'll see where this destabilization comes from. That was Slutmill's question. Okay, so what's the idea? So let's say I want to compactify this family. Then it's natural to look inside some Hilbert scheme. So what I'm going to draw in this picture, so this is my base curve C, same base curve. There's a closed point, there's a generic point. And what's on the top, this is inside an appropriate Hilbert scheme. Okay, so basically every family I start with give me a section of this Hilbert scheme, right? But I can know, but at the end of the day, I'm only worried about like the isomorphism clubs. So what I'm really looking at are the orbits. So basically, over a generic point, already what I'm going to put here is the PGL orbit of the point in the Hilbert scheme that correspond to the original Fano variety in my family. Okay, so already I have those to begin with. And I want to take a look at the closure of this orbit as t goes to 0. So in the closure, it might break down into several components. Okay, there's no guarantee about irreducibility, so I break down into several components. But because I have one way to extend this family, I know one of this component, at least it's another PGL orbit of x0 for that particular family. But there could be other components for different ways of fielding. Okay, so in some sense, this family is a section of this total space. But suppose that there is some other ways of filling in this family. That means there could be other choice of this section for some component in the central fiber that give me a semi-stable filling. And I want to find an algorithm to travel from this component to that component. All right, so there are two informations that allows me to do this. The first one is a theorem by Bloom, Liu, and Zhou that assuming this conjecture, okay, so let's assume that the delta invariant over there is computed by this. Okay, so I'll just write f instead of the order vanishing of f to save some letters. And this is at most 1. Then this divisor f is going to induce degeneration, test variation, right? So remember that the reason we are so interested in divisor variation is that they come from test variation. So this f, maybe not induced, but it come from a special test configuration. So this means that central fiber is irreducible KLT Fano. Of my Fano variety with a central fiber x0. So and moreover, this particular family has the property. Well, this particular degeneration of the Fano variety has the property that the delta invariant remain the same. So basically what I'm doing here is that, so I take my Fano variety, I take a device that computes the delta invariant, I can write down a test variation, but because the test variation usually carries this GM action, so I preserve the delta invariant, while at the same time, I'm also making the automorphism bigger. Okay, so. Yeah, equal. Yeah, so x0 is the degeneration of x. Okay, so you should think of this as, so I start with somewhere here, and increasing automorphism usually means that I'm going to a deeper stratum. Okay, so this is the first step, like this arrow. Usually it's going to increase. Yeah, usually it's going to increase. So if originally it already has a GM action, then maybe x is equal to x0, but that also tells me usually that this section is only at the center of this stratum. So what I'm trying to do here is that so suppose I have this section. It's in the middle of some stratum. I want to know, right? So and then there's another stratum I need to get to. So I'm going to go to the boundary, go to another stratum, go to the boundary, go to another stratum. That's the only way to go. Okay, so this first step is how I go to the boundary. Okay, and the second piece of information is that this was proven by Bloom and Liu that so this delta invariant is lower semi-continuous in family. Okay, so putting things together, that means, right, so this one, maybe it's not K-semi-stable. That means I have the optimal destabilization. I can use that to go to the boundary. Delta invariant stay the same. And I can deform into the second component. Delta invariant usually increases. If it's still not K-semi-stable, I repeat the same thing. But in this whole process, this delta invariant is not going to drop. Okay, so basically what they show is that after finitely many steps, it's going to be semi-stable. Okay, you cannot continue this indefinitely. So,
which one is the optimal? The first or the last?
So the first one, this is the optimal destabilization. Okay, so to compare with the vector bundles, okay, so maybe some of you might complain that this looks very different from the vector bundles algorithm. Okay, so just for comparison. So the Langton's algorithm in some sense can be thought of in this way. So originally you have this family of fill-in with central fiber E0. We have a destabilizing subbundle. And the way you get to this E0 prime is by first degenerating this E0 to the direct sum of F with G. So this comes by some extension class. I can specialize that extension class to 0, but then I can deform it using a different way of the extension. Okay. And when I deform it, I arrive at this E0 prime. Okay, so this is x1 of maybe F by G, but here I'm really looking at x1 of G by F. And that's the similar picture here. Okay, so I want to first do a degeneration and then deformation. I just have to make sure that in this process, the stability information I care about does not get worse. Okay, so but of course, it's the main idea. There are a lot of tiny things you have to show. For instance, we have to show there's some other components waiting there, so you can deform, etc., etc. So I think the actual proof uses this notion of theta stratification that was introduced by Kähler-Einstein, and the properness criterion originally developed by Kähler-Einstein and Heinloth. But I think that's too technical to write down. So that's the idea. Right. Questions? Okay. So.
Low semi-continuity is the same like the low semi-continuity for the
Log canonical threshold.
canonical threshold.
Yes.
Known for color by color divisor.
That's right. That's right. Yeah. Yeah. It's like log discrepancy over vanishing order is like a log canonical threshold. Okay. So what else do I want to keep? So I can erase again. Right. So. All right, so I guess we're happy that so at the end of the day, let's summarize. So the upshot at this point is that so this optimal destabilization conjecture implies both the Yau-Tian-Donaldson conjecture. It also implies the at least the k-stable part of the Yau-Tian-Donaldson conjecture. Also the properties of the K-moduli. And so, of course, one of our main theorem, just joined with Chen Liu, Chenyang Xu, and myself, so is that this optimal destabilization conjecture holds. For any KLT Fano varieties, so particularly implies both of this. But I haven't explained the finite generation part. Okay, so let's try to get there. All right, so how are we supposed to prove something like this? Well, so if I know that this invariant is computed by some divisor variation, and these dividers are supposed to come from some test configurations, then maybe I can try to pretend that oh, sorry, there's one other thing I need to first mention. So first of all, this invariant is defined as an infimum, but again, as I try to emphasize at the beginning, that this valuation space is like a limit space for all divisor variations. So this infimum is already a minimum on the valuation space. Okay, so this was proven by Blum and Johnson. That so this delta invariant in any case is computed by log discrepancy over vanishing order for some valuation. We just don't know whether this valuation is divisorial or not. Okay, but assuming it's divisorial, and let's pretend it's divisorial, so then we can try to write down that test configuration that is supposed to come from. So if V is divisorial, then it's going to come from a test variation, and this is how we write down the test variation. Then it comes from this test variation, where, okay, so again, T is the parameter on the base, and all right, so I need to do several things first. Okay, so first of all, when I have this valuation, I can write down a filtration on the section rings. Okay, so the section ring is the direct sum of all the pluri-anti-canonical sections. And this filtration is something that's similar that what you have heard from Andrea's talk, so I have lambda on this section ring. Maybe let me just write it down on the graded pieces. It's just And it consists of all the sections such that the value of this section is at least lambda. Okay, so, and then once I have this filtration, I can write down the so-called risk construction. Okay, so let me just use this notation instead of using the section ring. T minus lambda, direct sum of everything. So for divisor variation, of course, these are just integers. And I take the product of this. Okay, so when t is not 0, I can always divide by t. The filtration doesn't matter to us. I'm just getting the section ring itself. So the product is x. But when t is 0, then I get some finite structure. Okay, so then this gives me a degeneration of x into x0. And what's x0? Well, so there I cannot divide by t, but if I multiply by t, so then x0 is the product of, right? So this thing modular t times itself. So so what you get is, I think I need a bigger space. Let me write on the top. So then what you get is the degeneration of x into x0, which is the product of the following algebra, which is right. So if you multiply by t, I get f lambda divided by f lambda plus 1. So in other words, I get the graded pieces. Of this filtration. And then I take the direct sum. Okay, so that's what I'm supposed to get as a central fiber.
So this has many components?
Not really, depending on, so actually if it comes from like a divisor variation, then the property of the variation guarantees that this is integral. Because it's like, if f(x), it's just a corollary of this property. That when you multiply two things, it cannot. So when you multiply two things in the corresponding graded pieces, the v value of the product is what you expect. So it cannot jump.
How does it work? Divisor determines this algebra with x0.
Yes. Yeah. So basically, like, so this is how to go from. So I think earlier I mentioned how to go from a test variation to the divisor variation, and this is how you go from a divisor to the test variation in a more precise way by writing down this approach. Okay, so.
Fiber is integral and also KLT.
Not necessarily KLT, but at least it's integral. Okay, so. Yeah, question.
It's not negatively graded, right?
Yes.
Is M the grading or lambda?
So M is the grading. Yes, that's how you get the polarization. Yeah. So M gives you the grading plus the polarization. This lambda really gives you the GM action. Okay. So all right. So this construction, of course, looks very nice, except that so let me give this algebra a name. This is called the graded algebra of the section ring associated to this valuation. So I can do this even without So even if this is just a general valuation, I can write down this construction with the problem that if I want to actually get this algebraic variety, for instance, this has to be finitely generated. Right? Otherwise, I cannot take the approach. And so this turns out to be one of the major steps that we have to overcome. So the actual theorem we prove, and just perhaps the first theorem that you found in our paper, is that if the delta invariant is less than or equal to 1 and is computed by some valuation. Well, actually, you can do at most n plus 1 over n, but for us, the interesting part is when it's less than or equal to 1. N is the dimension. Then this graded algebra is always finitely generated. So then in that case, we don't necessarily get a test relation yet. We get a family, isotrivial family over like a bigger toric variety. And then you can choose a one parameter subgroup of that torus, which basically comes from like a point in the corresponding toric fan, and that gives you a test relation. And it turns out that this log discrepancy over the expected vanishing order is like a linear function in that fan. So
the dimension.
And it's the dimension. Yeah.
And so you are in projective.
Yeah, projective. X is the Fano variety.
Yeah, but in a projective space, not in weight.
Maybe
it's the same
which
thing
way?
in weight projective space, but you need to multiply by some of the degrees.
So
it doesn't matter. So the question is, X is in a just usual projective.
so I'm yeah, you can think of that way. Yeah. Yeah, it's I don't choose any particular embedding to start with. So
And if it's bigger, then it's stable. If it's not,
yeah. So if it's bigger than 1, then it's already stable. Yeah. Right. So anyway, so at the end of the day, what happens that so this will imply the optimal destabilization conjecture. Okay. And the rough reason is that so you write down some family over a toric variety, and then every one parameter. So the one parameter subgroup will give you a test relation. The one parameter subgroup corresponds to points in the corresponding toric fan, and this function is linear on that toric fan, which is a general corollary of this finite generation statement. And then the infinum of two like quotients of linear functions with rational coefficient, of course, will be a rational point. So that's the rough strategy, but that's what I want to get to. Thanks.
the reason that I asked that there are some ways there is because I've seen in papers of Yau-Tian and so in weighted projective spaces and so this inequality when it comes to weighted projective spaces actually you multiply by usually by the first two weights, the weighted projective space. In your case, they are ones.
I guess you are talking about like hypersurface, weighted hypersurface and weighted projective space, and then you look at some alpha invariant, etc. Yeah.
I have a question. So you also can look at this from equivariant birational point of view. You have a trivial family, like a product, X times C, and you have C star action, standard one. And you want to have C star equivariant fiber-wise transformation of the total space. You just change one fiber. So what this theorem, for example, means in terms of equivariant birational transformation, fiber-wise transformation.
So
it means you have finite limit.
Right. So what happened is that so when this is less than 1, right? So in terms of this compactifying the modular space, so that's when we have to change the fiber. So when this is less than 1, then we know this divisor variation is invariant under the automorphism group. So then the induced test relation also carries
of the full automorphism.
Yeah, of the full automorphism group. And then that degeneration family will also carries that actions of the full automorphism group. So everything descends.
So what do you need to get to in order to get the X0 not to be zero?
So then you have to choose a different filtration, not coming from a divisor. So you have to. So what happens is that so each component in the test relation, central fiber of test relation will give you a valuation. So if you only choose one, then you are supposed to only get one component. If you choose several and write down the correct filtration, then you will get several components.
But so then some of these pieces is not stable, and so that's no way that it stabilizes.
So okay, so usually if you have several components, then so you can run MMP to contract the components, and it turns out that the Futaki invariant, etc., they just decrease along the MMP. So higher Barab doesn't really give you extra information for Fano varieties. That's very special for Fano varieties.
Very general
Very
question.
nice talk. I've got to run.
Okay, yeah, thank you.
Very general question. In characteristic P, what is known?
Well, we don't know MMP in characteristic P.
No, we know something.
Yeah, we know something. Yeah. But let's put it this way.
For example, K stability we can define.
Yeah. I think like all the definitions makes perfect sense. Just log discrepancy, you can do it in characteristic P. Expected vanishing carries over in characteristic P. And of course, you have to assume some MMP. But there are also let me see. So there are several things here. So for instance, for this proof, we need the boundedness result. Like in some sense, the boundedness of Fano varieties in the flavor of Wilcar. And also the boundedness of complement. So actually, I didn't mention anything here, but actually to get to here, you need invariance of plurigenera. You need boundedness of complement. You need boundedness of Fano varieties by bounding the alpha invariant, which is already pretty close to Betty-Ref's conjecture. So bounded Fano index implies boundedness. Yeah, so Ref's complement. Yeah, etc. And I'm pretty sure at some point you need vanishing.
For example, criterion.
So that was based on like the MMP. Right. And also semi-stable reduction. So yeah, so there are many ingredients that are still missing in characteristic P. So, but of course the definition makes sense. And of course, I think we should expect the same picture to hold in characteristic P, but who knows?
All right. Thanks a lot again.
Yeah, thank you.